Hello, everyone. We're back again here at InfoAge Science and History Museums. My name is Jeff Brace. I'm a volunteer here at InfoAge. I mostly work out at the Vintage Computer Federation, but I help in many other areas, such as this talk, which is for ISEC, which is the InfoAge Science Exploration Center. Again, we have today Frank O'Brien, who is the technical director at ISEC, which I explained before, and NASA Solar System Ambassador. So welcome, Frank, again.
Well, thank you. Thank you. This is always fun to be here, and we're going to be learning a lot today.
Yes, and the topic today is origins of the moon.
One of the things that is probably been the big question thousands of years ago is we have a moon. We look up, we see it. Where the heck did that come from? And that's always been a question up until more recent eras. That really baffled us back in the day. We're going to trace through some of the history of that, and then how the moon, we truly believe, how the moon actually existed, and then what's happened since. And it takes some interesting twists and turns, so I think we're all going to be a little bit entertained. So, Jeff mentioned that I'm a NASA Solar System Ambassador. This is a fabulous program. We have about 1,200, give or take, volunteers, all volunteers, we don't get paid by NASA, that go out into the community to spread the NASA gospel. This is a wonderful education, public outreach, STEM activity kind of function that only NASA can do as well as it does. So I've been doing this for almost 15 years. I give lectures every month, once a month here at ISEC, and it actually is one of the best deals in government, because we don't get paid, you don't pay anything, and with the exception of one or two people back at our mothership at the Jet Propulsion Lab, no tax dollars are spent on it. You can't beat that as a deal. So anyway, way back before recorded time, mankind, womankind, probably even the animals looked up and goes, what the heck is that big bright thing up there in the night sky? And of course it was the moon. And it was always a presence there for, again, as long as they existed. But eventually, as consciousness expanded, someone asked the silly question, well, where did that come from? And how did it get to be? And so we're going to trace some of that history. And then we're going to trace, again, what happened and what's happened since. There's a lot of interesting things going on. Way back in the day, the stars were fixed in the sky. The ancients had in their mind, there were just crystal spheres with little holes in them that let the light through at night. Made sense. No way to test it, no way to disprove it. But the idea that that was inviolate was a key part of it. The Catholic Church totally latched onto this. This is God's design. We are not going to interfere with what God has said. This is the way it is. And this was dogma for hundreds and if not thousands of years. We had some radicals. We had this perfect view of the universe, but there were some disruptors. In particular, Johannes Kepler in the 16th century, who was an astronomer, and doing what astronomers did at the time, since we didn't really have much in the way of telescopes. We didn't have any telescopes at the time. But they were very good at measuring things, measuring the positions of the stars and planets. If anything, this was how you navigated, using the stars and such. And he noticed a few oddities. This perfect celestial sphere, these perfect crystalline spheres that the planets were attached to and going round and round, weren't so perfect after all. And through the work of Tycho Brahe, who also was collecting data, Kepler and Brahe realized that these are not moving in circles, but ellipses. This is not the perfect universe that the church advocated. This was really disruptive. I mean, now God is wrong. And calling out God was a bad thing with the church. This got worse years later when Galileo started doing his observations with a telescope. And now he's seeing that the moon isn't this wonderful sphere. It's got mountains and craters and et cetera, et cetera. Jupiter had moons. We have the 4 Galilean moons, as we call them, the 4 big moons. And the church didn't think that was a very good thing. The sun, this perfect, wonderful ball in the sky, had spots on it. This was disruptive. This was not the way the world is supposed to be. But over time, we started realizing that there is a scientific method. The whole Industrial Revolution was predicated on that. Mathematics exploded. Newton came along not too terribly far after that. And so we started thinking that, instead of like magical spheres and all the rest, the solar system, after the star was, after stars, our sun in particular, were formed, there's still tons of material that are going around and around. And with that, gravity always wins. And little pieces start to collect into bigger pieces. And bigger pieces collect more. And eventually, you have planets. This is called accretion. As they're going around, you collect more and more stuff, more gravity, everything starts combining. And voila, you have a solar system. But all this is wonderful, but this doesn't explain how the heck we got a moon. I mean, these are wonderful theories, and we're very, very comfortable with it. And actually, we do see these kind of phenomena happening in the universe now with our telescopes and the Hubble and all the rest. But how the heck did we get a moon out of all this? Well, the scientific method makes us think about certain criteria, things that we have to be able to explain. First and foremost, the simple basic things. Does physics allow this? You just don't pull rabbits out of a hat. You have to be able to show, with the equations in science at the time, if this makes sense. We know from the Apollo missions a couple interesting things. One of them was the isotopes of oxygen. Yes, the oxygen you breathe, it's all made up of, you see it in oxides and rocks. The isotopes, which is a fantastic way of identifying materials and determining their ages, we found out from the Apollo missions that those are identical on the Earth and the Moon. That means something. If it was created elsewhere in the solar system, those would be very different. And we do see that on other planets. The Moon doesn't have a large iron core like the Earth does. Compared to, the Earth is far, far, far more dense. We have to come up with a theory that explains why there's no core on the Moon. Again, from Apollo, we put a bunch of seismometers on the Moon. We looked at what we were hoping to see, and we didn't see it. We didn't see a core, or a very, very small one for all intents and purposes. Also, we now know the Moon has very few volatile compounds. These are compounds that, under heat and pressure and all the rest, just outgas. They just go off into the...
What's an example of one of them?
Water.
Water. So it evaporates.
You heat up enough water, it evaporates and goes off into space, as one example. We have a whole category of what we call ices. We'll look at carbon dioxide. We know carbon dioxide, dry ice, that is its ice form. You put enough warmth on that, off it goes into space. So there's lots of examples, this being the simple, easy ones. More complex molecules have their own examples. Now, the other thing is, the Moon is in a pretty boring, stable orbit. Almost perfectly circular, not quite. But we have to have a good way of creating a moon that's in a good circular orbit around the equator of the Earth. So these are the tests we have to go through. So let's go through and find out what people were thinking back in the day. Late 1800s. George Darwin. We all know of Charles Darwin.
Mm-hmm.
That was his dad. His son, George Darwin, was an astronomer in England, and he was kind of curious about this. And so he came up with the theory. Again, not having a lot of data, just more deductive reasoning. Imagine the Earth spinning very, very fast. And we know that if we have something on a string spinning it around, eventually maybe the string will break and the thing flies off. And he goes, that's the answer. We're going to keep spinning until a bulge happens on the Earth. It breaks off. Poof. We've got a moon. People are going, that works.
Did he also think that maybe if the moon broke off like that, then the Earth slowed down at that point so that it wouldn't?
I don't know that. I don't know that. But that would make sense when you look from a perspective of angular momentum, because now the moon is flying off, takes all that energy with it. But it turns out there's a few problems with this. What's a good example of an everyday example of things spinning?
Car wheels.
Mm-hmm. And those are pretty strong.
Yeah.
When you think of it, you're going 70 miles an hour, and you don't have a blob of tire flying off, unless it's a bad day.
Yes,
but it does
tires
happen.
Damaged. Yes.
Okay.
Um,
Something just as common.
Ah.
Now we have a bit of a problem with this theory. Here we said, oh, the Earth is spinning, going really fast. A chunk of blob pops off, whatever, but that's not the way spinning objects work. Think of like when they're spinning a pizza.
Or maybe a pottery wheel, something like that.
Exactly.
That's another reason.
Exactly.
Yeah.
You're going to get a smooth, even surface. Unless there's some oddities in it, it's not going to throw off a chunk. It's going to spread out. Now, the speeds that he calculated, now we have to talk about the basics of physics. He predicted that in order for this to happen, the Earth would have to be spinning quite a bit faster than it is today. And he calculated that it would be a little over 2.5 hours for a full day. Again, this is the best you can come up with. We didn't know orbital mechanics at the time. We really didn't. It turns out in order for something to go around the Earth in a stable orbit, you have to be at least close to the Earth. Go up. The Earth has to spin in about an hour and a half. Now, can you imagine a day and a half? I mean, that's the time it takes to orbit, say, the space station. 90 minutes, give or take. Now, can you imagine day and night, a full day being only an hour and a half?
That'd be like a film of the sun going very fast.
Oh, yeah, it would be like a time lapse. And more importantly, we would be thrown off the surface, more than likely.
Oh, boy, yeah.
And so there'd be no one to report on this. So that didn't work out very well. The physics didn't work. The stable orbit didn't work. We didn't know, of course, anything about volatiles. And
So the first attempt's a idea, but when you apply the
Yeah.
physics to it, which weren't really known at that time, or maybe he wasn't very well versed, then it doesn't hold up.
No. But at first glance, it's like, oh yeah, that'll work. Well,
Yeah, just as a
first guess.
First guess, it's a good guess, but if you're not well versed, it's like, all right, well, you thinking about practical examples on the Earth. Oh, that makes sense. But let's check.
And
it out.
again, this was the days before a lot of the scientific rigor that we use today was able to be applied, because we just didn't have the tools or the instruments to do that. But it made sense. And it's like, okay, that'll work. We don't have a better idea. But eventually we did have better ideas. And one of them was that, well, we had the sun, and there was a disk of gas around and materials eventually forms the planets. Some smart guy goes, well, the Earth or a planet has gravity. We know that lots of planets have moons. I'll bet you they had their own disk going around. And from there, the moons formed. And that works. That seems to make sense. And here's a photograph of what we see. This is from Hubble, of a moon going around its planet. And you can see the dust bands and all the rest that it's gathering material from. That is, the physics works. The physics works very, very well. The stable orbit maybe might work. But we start getting into those interesting problems that you'd only be able to know since Apollo. If you're forming in a different region of space, your material composition is going to be very, very different. You're going to have lots of iron. You're not going to have that same oxygen ratio. You're probably going to be able, because there isn't a lot of heat involved in this, you're probably still going to have all those volatiles. Ooh. We got 2 check boxes, but the others don't seem to work.
Yeah, another plausible theory, but when investigated.
Again, for lack of any other ideas,
yes.
it seemed to work.
Yeah.
So smart people went back, and we do know the next thing does happen. What would happen if some body in space comes by the Earth?
Like we get comets and other things, and maybe earlier on in the solar system's history, there was a lot more going on.
Oh, there was a huge amount. We're going to be talking in depth about that in a bit. But, a body in motion stays in motion. Yes, it's all going to get twisted off to the side because of gravity. But you don't have an easy way, from a simple example like this, for a big rock or a moon to be captured. It's going by. There's nothing slowing it down. It's going to get curved because of gravity, but how would we grab onto something like that? And it turns out the solar system isn't nearly as simple. We're going to get a little bit crazy in this, but this is important. And this is actually a key part of it. This is what you might think of as a map of the gravity around the sun and the Earth. You have these gravity wells. But it turns out when you do the arithmetic, there's certain regions in space where the Earth and Sun's gravity cancels out. And you can just kind of hover there. And they're called Lagrange points. This has been known for, 100 and 150 years. Well, we actually use these every day. The Webb telescope and a couple other big telescopes, we want them far away from the Earth because we don't want the heat and all the rest of it. We want them always visible. We don't want to have to sit there and wait for it to pass overhead. We need it parked. And it turns out these points are perfect for that. We have we have Webb out at what's called the L2 point. We have lots of satellites watching the sun for solar flares and such at the one opposite in between the Earth and the sun. And they just go in a slow looping orbit, if you want to call it that. But effectively, they're hovering there in space. And this is a quirk with gravity. And as you look deeper, you realize it almost is like a skateboard park with all kinds of hills and valleys that you'll go up and down in. To the point where, again, we say we have the moon, as if it's the only moon. Turns out we have a bunch of them. And one of the things is, because of this quirky skate park world of gravity, rocks coming by the Earth will temporarily grab one. And you can see the path. It's obviously not the crystal spheres of perfect orbits, just the way it, again, like in a skate park, going around up and down these gravity hills and valleys. It is gravitationally attached to the Earth, but it's certainly not going to be permanent. And so over a couple years, this is, I think, from 2024, we grabbed a passing asteroid. It's going to be bouncing around the Earth a few times, and in a few years it's going to go bye-bye. I think right now we have about 2 or 3 of these little mini moons, all doing this crazy dance that again, I don't pretend to understand the math. I know smart people do, and all the modeling and simulations seem to work. But, okay, could we have captured the moon this way? Well, we have the same problems with the co-accretion theory. It's coming from somewhere else, the isotopes, volatiles, all the rest don't work. We don't have a stable orbit most of the time. And, yeah, the physics does work, sort of. So, again, a wonderful idea, smart people worked on it, it didn't go.
So one of the differences between these mini moons is the mini moons are much smaller, whereas our moon is quite massive.
Right.
And it would take a lot more. It's too big to be captured by our gravity.
Ooh, I'm not going to go that far, but it would probably be a lot more complex because instead of a little mini moon, which is probably a couple miles on a side, we're talking something 2,000 miles with a non-trivial amount of gravity of its own.
Yes.
And so the interactions are going to be very different. It wouldn't look like that. I don't know what it would look like, but you can bet it would be equally chaotic.
Yes.
So, smart people again, sit down. We came up with an idea. We think we have the answer now, where the moon came from. And it's called the Big Smack. Hey, these are smart people. I mean, you can imagine over adult beverages, they came up with it. Technically, it's called the giant impactor theory. And what is theorized, again, this does check all the boxes. We think that another planet, maybe the size of Mars, smacked into the Earth. And from that debris cloud, launched into space, ooh, that could turn into the moon. Now, this is a wonderful, super dramatic picture. The problem is it's all wrong. What really probably happened is that it was a glancing blow. Because if something hit head-on, both would be destroyed and we'd all be floating amongst the rubble and there wouldn't be us to be around anymore. But that then makes you still wonder, okay, what's the physics of this looking like? And that is where we get into some rather clever videos. Again, smart people do this. Here we have a video. And the one wonderful thing is that they have done a lot of hard work on this. And you see, because these are molten objects, mostly, you don't expect the Earth to be so fluid like that, like, hitting it. Theia, which is the name of the body that hit the Earth, is what we've named it, forms two objects. The big one is probably the core of Theia. And it gets reabsorbed by the Earth. It explains why the Earth has, comparatively, such a large iron core. You also see as the gravity affects it, they start getting distorted. And of course, it's almost like a bag of water or a balloon of water. But as they go and get smacked, big piece and a small piece, one of them gets to be the moon. And again, this is more chaotic and violent than we could possibly imagine. Imagine the entire Earth being liquid, just a big droplet in space. Not a good place to raise kids. Now, let's talk about those check boxes. We know the physics will work. Impacting bodies we see all the time. And the way they've done their analysis, it really does look like this will end up in a stable orbit. Those are two big check boxes. The physics absolutely works. Remember, these are molten bodies. You're not going to have any volatiles. Since it's coming from the Earth, or a combination of Earth and Theia, they are going to have the same isotope ratios. And, as we noticed, it's a grazing impact. It's just ripping off the mantle and the crust of the Earth, not the core, at least just a very small part of the core. And what's left of Theia ends up getting absorbed back into the Earth. So the moon, which compared to the Earth is quite a bit less dense, it checks all of those boxes as well.
So what time period are we talking about when this happened, and what was the Earth?
About 100 million years after the solar system formed.
Oh, so
And-
very early.
Oh,
So,
very, very early.
So about 4.5 billion years ago.
We'll say 4-ish. Again, there's a big range. One of the problems is it's difficult to date rocks once they've been melted and reformed. The moon is great for a time capsule because it cooled so quickly. We're going to get into that. The Earth took a lot longer. And that's why it's difficult, not impossible, it's very difficult to find incredibly old rocks from the beginning of the solar system. We will see them on the moon, something like 4.3 billion years, but the Earth was molten for a couple 100 million years, and that's actually part of the rest of the story. So the oldest rocks we'll see are 3.84 billion years, although, yes, there are some that are a little older. So, we wake up and we go, what the heck was that? What just happened to my Earth? And surprisingly, that whole process of creating the moon, that impact, only needed a couple days, if not hours. Remember, things are going very quick, very violently. Yes, everything was still molten.
Yeah.
The actual impact wasn't something out of Hollywood, melodramatic, where it goes smack. Your relative speeds, it was probably in almost an identical orbit to the Earth, and so it's overtaking. But when you look at the sizes and the scale, it probably took 5, 10, 20 minutes for it to scrape off a chunk of the Earth. That's almost bad science fiction slow motion. But we'll say it's 5 minutes. Well, that's still pretty quick.
Yeah.
And that's enough velocity to fling something into an orbit. So the scales are, again, if you're expecting a Hollywood, boom kind of impact, it didn't happen that way. But now, here we are. How did we get here? And what just happened? Where did this Thea come from?
Yeah, well, that's a big question.
No, it's not. This is the second part of the talk. This is the fun part. Where the heck did Thea come from? Sounds like name for a bad movie. Maybe we could talk. All right. Why were we getting bumped by a small planet? Again, we're thinking about the size of Mars, maybe.
Yeah, very big.
Well, it was a very busy, chaotic time in the solar system early on, a couple 100 million years after all this was formed. And we all know that version 1.0 of anything is not specific, not particularly stable on multiple levels. And so 4.3 billion years ago, we got ourselves a solar system and a star. We call it, the sun. And boy, check that off. We made a solar system, version 1.0. There were problems with the early solar system. This was probably not figured out in a design review, I'm sure. It turns out it was very unstable. Now, remember when we were talking about capturing an asteroid, these little hills and valleys of gravity, just like a skate park. So we're comfortable with the idea that gravity can affect the path and interact with other objects. That's the nature of gravity. So, it turns out the early planets, which formed quite a bit closer to the sun, started interacting with each other. And when they start interacting, now we're talking Jupiter-sized objects. We're not talking a little rock a mile or two. When we do calculations for trips to Mars, we have to calculate Jupiter. It's in there to a few decimal places way to the right, but yeah, it's in there. Now you look at that over millions and millions of years. What do you think the effect is going to be? And it turns out, when you have an unstable solar system, Sounds like a name of good.
Yeah.
Sounds like a name of a band, actually.
Define unstable.
Right now, we have a stable solar system. We use this as one end of the argument, and everyone's happily going around the sun. And there might be interactions, but there isn't any interactions that are so strong it's going to truly disrupt the path of the others.
So in other words, like stable orbits,
Yeah, everyone is in their own little world.
Pretty much predictable orbits.
Exactly.
Okay.
And things that more than likely are going to last for hundreds of millions of years. This was not the case right after Solar System 1.0 came out. And because of that, we're very comfortable with the idea of resonance. Things that start building and compounding on one another. We have feedback in audio. That's resonance. As things start interacting, they get constructively louder and louder, for example, in feedback, or destructively, getting quieter and quieter. Here, we had destructive resonance in the solar system. And what happens when you get a lot of planets interacting with one another through gravity? The original solar system was not the same thing we see today. All the planets were quite a bit closer to the sun, and Uranus and Neptune were reversed. Now, we're not going to go into Star Trek or Star Wars and all the rest about how you move planets around, but that's a tough job.
Yes,
Over time, gravity wins. And so this is a model developed in Nice, France, where the big astrophysics convention was. A bunch of guys got together and said, well, what if? Because so much stuff is not easily explained. In the longest sense, where did Theia come from? Why does the moon have so many craters? These are all related. And it turns out this Nice model, again for location Nice, France, we started looking at the early solar system and how everything interacted. Here we have Jupiter's orbit, Saturn, Neptune, gee, that's in the wrong place, and Uranus. What happened? And we had the Kuiper Belt. This is where a lot of the rocks and junk in the solar system actually resides. And as we start moving forward from its creation, yeah, those orbits look a little sketchy, but all of a sudden they explode. And Uranus and Neptune switch places. And you notice that, first off, that whole Kuiper Belt is now completely cleared out. Also, the planets are far more distant from the sun. Their interactions are now far more limited, and so they're not interacting, and there's stability that resumes in the solar system. And we can take a look at it again.
Oh, it's going through. The time is millions of years.
Yes. But with all of these bodies, these Kuiper Belt objects flying around, one of them was probably Theia. And this is what's called the late heavy bombardment period. You have rocks flying all over the place, not in nice little stable orbits. And because of that, you have a little problem. Everything is getting hit with meteors, with big rocks from space. Now, at the time, the Earth is still pretty much molten. It's going to get hit with a rock, and the rock just goes splash. The moon, being much smaller, cooled far faster, and so it preserved that history of impacts.
So it cooled faster because it was smaller.
Much smaller.
So
less heat.
Something about thermodynamics to cool faster.
Well, it's a square cube law. It's much smaller. Its volume was less, had less heat to dissipate, and when it did, the Earth being much, quite a bit larger.
Yes. All right, makes sense.
So the moon preserved the record, if you will, of all these impacts. And we see that when we look at a gravity map of the moon. We took this about 20 years ago. A mission called Grail or Grace, one or the other, that did wonderful gravity mapping. You know, the scientists learn a lot. And we see that there's big red spots, especially in that northern half of the near side, where big impactors hit its semi-solid moon, and a big chunk of them is still probably in there. And that's a big, heavy rock, probably with all that iron and all the rest that the moon was not made with.
So is a higher gravity because there's iron? Is that what's causing the higher gravity?
One explanation, yes. And it could be something that's low mass, getting all the blue, but we have what's called the South Atkinson Basin on the far side of the moon, that it's less gravity just because whatever impactor was there took out such a huge chunk of the moon. It's actually a very shallow valley. There's not as much moon there for gravity to be pulling on. So if we match up a lot of those red areas, they kind of match up with the seas. And so when these impactors hit, these huge, huge rocks, certainly miles and miles on the side, they hit with such force that it liquefied the surface again. Not the entire moon, but hit tremendous amount of kinetic energy, lots of heat. And so the surface melted again, flowed over all those mountains that existed, and now we have relatively smooth seas, for lack of a better phrase, the Maria. And so this bombardment lasted tens, if not hundreds of millions of years. And that's a long time to be beaten to death, but it didn't stop. There wasn't a hard, oh my God, we're done with this, ending to it. I love this picture. This is the central peak of a crater called Tycho in the southern hemisphere of the moon. You can see it easily from Earth. With not even a powerful set of binoculars or a telescope, you can see this mountain at the very center of it. This rock hit so hard, it pushed the floor of the crater down and it rebounded up into a mountain. This is only 100 million years old. In the history of the universe, that's just a blink of the eye. And we see the effect of cratering even today, relatively speaking today. We certainly saw what happened in Russia about a decade ago. Meteor crater in Arizona. If you ever get a chance to see it, it's impressive. It's a mile-wide crater. That was only 50,000 years ago. That just barely makes it into recorded history. So this kind of meteorite impact
is continuing and
has
continued up until relatively recent times in terms of a cosmic scale. 100 million years is smaller compared
it's a blink
to
of the eye.
4.5 billion, yes.
And we have, mostly amateurs, have telescopes focused on the moon looking for impacts. And this is one that happened last year. And something hits the moon, big flare, probably some molten material. They record these even today. And that brings us to the present day. The moon is still evolving.
Still being impacted by various meteors? Right?
Yeah. Well, I will say asteroids, because meteor is something that burns up, it goes through the atmosphere and burns, but yes.
So a lot of what you mentioned before about the isotopes, we had gotten a lot of that information from the Apollo missions that brought back rocks, so we can actually examine the materials.
Yes.
And they I think they brought about 48 pounds. Is that, or how many?
That was only on the first mission. In total, it was about 840 pounds.
And
so we have almost a half a ton of moon material.
And they took samples from different. From one of them was Sea of Tranquility, and did they take it from different parts, just sort of to get a more diverse sample?
Oh, completely. The whole idea was they spent a lot of time thinking about what would be a representative location to answer certain fundamental questions. One of the landing sites, we talk of the crater Tycho, which when it hit, it was so big that it just sprayed out material for hundreds of miles. There's another one called Copernicus, also on the near side. And so the second moon landing was designed to land in one of those areas where the material was sprayed out. The idea is, we can grab stuff on the surface, comparatively easy, but this stuff coming up and being spewed out is probably from deep interior stuff. We can learn a lot from that, and they did. We landed in the highlands, in the rocky parts. Those are always tough, but the miracle of Apollo is that we were able to go to such diverse sites. As a matter of fact, when we talk about the crater Tycho, in the early planning, when we were supposed to go back to the moon many times more than we did, one of the missions was to go to Tycho. And budgets and all the rest, we know how that went. That would have been an extraordinarily difficult mission. And it might not have passed muster because it was so difficult.
So they're still continuing to get more samples, more evidence from different parts of the moon, just because there's different features that would give you more evidence of the Big Smack theory.
Well, I think we're all pretty comfortable with the idea that the Big Smack happened. Now we want to know the downstream effects. And believe it or not, one of the most, and it's difficult to say these words because they're not 100% true. One of the difficult things is that we actually get lunar material from China. They have, and again, we can go back and forth on this, they have a tremendous lunar and Mars program, and it works really well. We can say a lot of things about China, but when they set their mind to it, it does go. They were able to land a spacecraft and a rover on the far side of the moon a couple years ago, and it grabbed samples and brought them back. No one's ever done that before. And because of that, we now, that South Atkin Basin, that looks so interesting, we now have ideas. And despite the current political situation, we did swap some of our Apollo samples for the Chinese samples. And it's all very much on the up and up. It wasn't, snuck in a suitcase or something through customs. But sometimes science is like that.
Intergalactic customs agents.
Yeah, there you go. There you go. But so we're able to see a lot of interesting things. And I don't have the details on what those analyses were.
So is there any others, it seemed to be this is the most plausible theory with a lot of evidence. Is there, what sort of things do they have to just find out just to solidify this theory even
Honestly, again, since it checked all the major boxes, it's tough for me to imagine what questions are left open. Yes, we can go back to the moon, and when we do, we might be able to find out more. But again, science is an evolving thing. First, we thought it was spun off, a piece of rock flew off of it. And then we did more analysis and found out that wasn't the case. Other good ideas at the time didn't hold muster. This is a really pretty good idea. It's holding up. What other things could you imagine have happened, or what other things could you imagine happening that would invalidate the Big Smack theory for something else? That's getting tougher and tougher to do.
All right, so this was a great talk. What will be your next talk? What will be next month's talk?
Well, Origins of the Moon. I'm stunned that it isn't front page news. We're going back to the moon.
That's amazing.
In a couple weeks.
Yeah.
This isn't, sometime in the future or in the next decade. No. They've set a date. This is getting close to the end of February. It's March 6th. If everything goes right. NASA had a major test, confidence building test, of the rocket and the spacecraft. They had that 2 days ago. It did very well. And that is a huge sigh of relief for a program that has had technical problems, ground support problems, etc., that are extraordinarily difficult to deal with. Not that they're not smart people, but these are just really tough problems. They think they've gotten around them. And the spacecraft looks good, the rocket looks good, and they have scheduled a launch, I believe, something like 8:30 at night on March 6th. That may move a little bit, and we have 5 opportunities in March before laws of physics say we have to wait a month. But we're going back to the moon. The first time in over 50 years.
So this would be a flyby with
Yes.
humans inside
Yes. 3 guys, 1 gal. One of them's from Canada. And it's all part of the idea that, at least from the U.S. perspective, this is an international effort. Remember, the Europeans built part of the spacecraft, part of the Orion spacecraft, what's called the service module. Canada has already committed to building an important critical part of a mini space station that we're going to be putting around the moon in the next many years. Europe, Japan, so many of these other countries are all contributing, and I would put money on the fact that maybe in the first moon landing we're going to have a European on there too. That's
great. It's exciting news.
Yeah.
And I appreciate you giving this talk. I learned a lot myself. I did some research, but I still learned some new things here. So thank you very much, Frank, for this talk. And I look forward to talking with you again at the next talk.
I can't wait. It's going to be a good one. And again, next month's talk, I'm hoping, if everything goes right, we're going to be talking about our mission to the moon.
That'll be exciting. I look forward to it.
And we haven't had an opportunity to do that in over 50 years. Think of
Yes, that's been a long time. It's overdue for returning. Well, thank you, everyone. Please
really appreciate you being here.
Share this video with everyone. Like it. Give comments. Also, if you have any ideas for future talks, we can come up with a lot of great things. Please let us know about that too.
Yeah, love to hear it.
And we always appreciate support, donations, or visiting here at InfoAge and the ISEC building and our radio dish, which is very popular.
And Jeff, I have to thank you. It has been a wonderful, wonderful talk with you.